Alright, we'll now work through these two examples on pages 12 and 13, and I'll leave the homework questions for you to use as practice. Okay, so an X-ray machine in a hospital accelerates electrons in a strong electric field and fires them at a metal plate. The electrons travel 5 centimeters, so that's the distance, and they reach a speed of 3 times 10 to the 7 meters per second, and we're given the electron's mass, and we know the electron's charge from earlier. Okay, so we have a distance of 5, and we have a V of 3 times 10 to the 7, and we have a mass of this. So we're given enough information here to work out the final kinetic energy of the electron, which will then let us go backwards and work out how much electric potential energy the electron must have had before it was accelerated, and that should allow us to work out the voltage required. Okay, so we used the fact that EK is equal to half mv squared, which in this case is equal to a half times 9.1, or 9.0 it says, times 10 to the negative 31 times 3 times 10 to the 7, which is equal to 1.35 times 10 to the negative 23 joules, and that must be equal to the change in electric potential energy. Well, the gain in kinetic energy must be equal to the loss of electric potential energy, and so we know from our equation earlier that that is EQD, or it's the voltage times the charge. So we know that V is equal to delta EP over Q, and in this case that is equal to 1.35 times 10 to the negative 23 divided by the charge on the electron, which we were given on the previous page. It's 1.6 times 10 to the negative 19. If ever you needed that in an exam, by the way, that will be provided, that information. So that should give us the voltage required. So it's that does not look right. And the reason it doesn't look right is that I forgot to square this. Okay, so let's try that again. This answer is not correct. So that's 0.5 times 9 times 10 to the power negative 31 times 3 times 10 to the 7. Let's all put brackets around that and square it. Oops. And it's actually 4.05 times 10 to the negative 16 joules. Okay, and so that is wrong. That should be 4.05 times 10 to the negative 16. And we divide that by 1.6 times 10 to the negative 19, which is 2531 volts. And to the correct number of significant figures, that should be 2, which is equal to 2.5 times 10 to the 3 volts. Okay, so my mistake there was not squaring the velocity for the kinetic energy. I knew that my answer was wrong because I got a tiny voltage, and it didn't seem right that we'd be able to accelerate an electron to that speed with that small voltage. Okay, calculate the electric force on the electron. Well, we know that F is equal to EQ. We don't have the electric field yet, so we need to figure that out. We can get that from E is equal to V over D, which is equal to 2.5 times 10 to the 3 over the distance, which was 5 centimeters. We need that in meters, so that's 0.05. So that is equal to, I'll use the unrounded number in my calculation, 50,625. That's the electric field, and so the force is equal to 50,625 times 1.6 times 10 to the negative 19, which is the charge, and that is equal to 8.1 times 10 to the negative 15, and force is measured in newtons. The electric field is newtons per coulomb. Okay, so that's the end of question 1. Question 2. A small particle accelerator contains an electron gun to fire electrons at high speed. It consists of 2 metal plates with a high voltage between them, and the plates are 1.5 millimeters apart. Okay, calculate the electric field strength. So E is equal to V over D, which is equal to, and we're told what the voltage is here, it's 5,000 volts. 5,000 over 1.5 times 10 to the negative 3, because millimeters is times 10 to the negative 3. So that is equal to 3.3 times 10 to the 6 newtons per coulomb. The electrons are pushed to the right by the field. What direction is the electric field? To the left. And that's because electrons are always pushed in the opposite direction to the field because they're negatively charged. Which plate is negative? That is the left. Oh, hold on. The left field, left plate. Calculate the force on an electron. F is equal to EQ, and that's equal to 3.3 times 10 to the 6 times Q, which is 1.6 times 10 to the negative 19. And we get 5.3 times 10 to the negative 13 newtons. Calculate the work done on an electron as it moves between the plates. Okay, work done is equal to force times distance, which is equal to 5.3 times 10 to the negative 13 times 1.5 times 10 to the negative 3. Um, 8 times 10 to the negative 16 joules. Determine the gain in the electron's kinetic energy. Well, that must be the work done. Using the work energy equivalence. Calculate the electron's velocity as it exits the hull. Well, we know that EK is equal, well, the gain in kinetic energy is equal to 8 times 10 to the negative 16 joules. And we'll assume that it started off at rest, so that's all of its kinetic energy, so that should be equal to half times 9.1 times v squared. So rearranging this, we get 2 times 8 times 10 to the negative 16 divided by 9.1 times 10 to the negative 31 should be equal to v squared, so we'll just square root all of that. So square root of 2 times 8 times 10 to the negative 16 divided by 9.1 times 10 to the negative 31 is a very high speed. 1, 2, 3, 4, 5, 6, 7, 4.2 times 10 to the 7 meters per second. Okay, so those are a couple of practice ones. You can have a go at these homework questions on your own.